Advanced sensor suites and machine learning have ushered in intelligent features in automobiles such as self-driving, collision avoidance, and auto parking. As consumers adopt these technologies, they naturally begin looking for similar features in other industries, such as marine applications. This is where our capstone project comes in. Today, we will be discussing our automatic boat docking system with multiple RGBD cameras. We are supervised by Professor Alexandra Albu. My name is Robert, and my team is Declan, Liam, and Daniel. According to the US Coast Guard, the two top accident types in recreational boats are collisions with other vessels and collisions with fixed objects. In a typical dock environment, these risks are much higher, as there are numerous other vessels and many tight spaces. The current boat control system does not provide adequate driver assistance features to improve accessibility and reduce these risks. The goal of this project is to develop a computer vision and control system suite to steer a GPS-integrated electronic boat control system into a dock. Our objectives are multifaceted. First, it should be able to track its location and automatically navigate to its target. It should require little to no user intervention, avoid obstacles, and identify safe regions within the water. Automatic path planning should also be performed. We have determined a number of scope-limiting details. First, our system will operate in good weather and water conditions. The current should be low, and the temperature should be moderate. Our system will only consider smaller boats less than 30 feet in length and assume a stationary dock environment for the first iteration. We will limit destinations to within 75 meters of the current location. These details improve the feasibility of the project within the limited time frame.
We have developed our system to integrate with an existing electronic steering and control system for boats. The existing electronic steering and control platform allows for full boat control in rotation and translation simultaneously, shown here. This ability is especially helpful in tight spaces expected in docking situations. This property allows our path planning to create complicated maneuvers for the electronic steering and control system to perform. We interface our module with the electronic steering and control system through a CAN to USB interface to send motion commands. Our system requires a computation core in the auto dock controller, which interfaces with an arbitrary number of cameras, only limited by USB bandwidth and available computation. To set up the system, each camera is first mounted in the primary camera 0 location, then recorded moving to its final location. This makes our system easy to install as either an OEM product or a retrofit kit onto an existing platform. Further, this system makes no strong requirements for accuracy of camera mounting position, or even the layout of secondary cameras. Each of these cameras report point cloud data using an existing stereo vision algorithm, which we then synthesize into a single point cloud. With this point cloud, we can then delineate obstacles and generate a 2D map around the vessel. Our system can detect arbitrary obstacles from the point cloud data using marine domain-specific properties. Here we can see on the right a generated map using two cameras. The map resolution is 10 centimeters, the white areas indicate obstacles, the blue areas indicate explored regions, the black areas indicate unexplored regions, and finally the red areas indicate the camera fields of vision.
Once the local environment has been mapped, a specially developed pathfinding and collision avoidance algorithm plots a course to the predefined GPS target location. Here, we see a mapped obstacle field on the left, with a path planning solution on the right. The vessel's current position is marked by the blue dot, and the target by the blue X. Notice that, while the vessel could arrive at the target via a nearly direct path, the path planning algorithm instead orients the vessel perpendicular to and centered on the obstacle gap, ensuring a margin of safety from nearby obstacles. Preliminary testing was conducted in a storage warehouse to simulate a marina environment. Here, a dolly with two Z stereo cameras is being manually maneuvered around the warehouse. Notice how the obstacle map changes as new obstacles come into view of the camera, but old obstacles do not disappear from the map. Here, the dolly is tilted to demonstrate the system's robustness against vessel motion and rotation. The path planning algorithm is adaptable to a wide range of vessel geometries to ensure a safe route is selected. On-water testing with our sponsor's test boat is planned for later this month.
We would like to give a quick summary of some of the features that make our product so novel and easy to use. First, the initial camera calibration is simple and intuitive, and the vessel only relies on the onboard cameras, a GPS signal, and the running software to operate. The system also operates in real time, allowing for dynamic responses to the ever-changing environment. The system map has a granularity of less than 20 centimeters and can be extended by up to 250 meters without performance loss. The cameras themselves each have a near 90-degree horizontal field of view and can return three-dimensional point data from objects up to 20 meters away. With regards to the path planning, the real-time nature of the system allows for continuous updating of the vessel's trajectory, and the pathing algorithm also factors in the physical geometry of the vessel when making decisions. Also, the continuously updated FOV map accounts for which areas have been observed by the cameras and allows the pathing algorithm to backtrack and explore unmapped zones if there appears to be no path forward. With that summary out of the way, here are our references. Thank you very much for listening to our presentation.